All right, check. Hopefully we're going live here soon. Maybe. Should be. Check, check. Hello, good morning, Carly. How you doing? Let's see. Some people to show. Okay, so remember, if you can't participate in the chat, send me an email and I'll answer your questions that way. Um, so today, I want to go over Unit 7, start Unit 7. Just the beginning. We can take our time with it. Because again, this is all optional right now, and we'll. Hi, Aaron. Yeah, no worries. I'll live stream again for honors at around 11:45. Okay, around 11:45 is when I'll be on to go over the practice test for honors. Okay, so today I'd like to start Unit 7, and again, this is all optional. We'll be doing this again once spring break comes back around, or at the end of spring break when we can officially start our distance learning stuff. And I'll be able to make stuff mandatory and actually assign some things. But for those of you that want to, keep up and, kind of get on top of the AP test, this is the last content that you need for this year's AP test. So remember, this year's AP test will only cover our units 1 through 4, and then it will be our unit 7. Okay, and if you look at the College Board classroom, that's the College Board units 1 through 7. Okay, so what will not be included is a lot of the acid-base stuff. So like acid-base, weak acid-base equilibrium, buffers, probably acid-base titration curves won't be covered, but the concept of titrations, doing stoichiometry calculations with the titrations data, that's still on there because redox titrations is still part of that. Okay. And so the last unit that we did, Unit 5, the acid base unit, that most of that stuff's not going to be on your AP exam. And then the delta G, the free energy thermodynamic stuff, and electrochemistry won't be on your AP exam. So I'd like to go through this content with you guys, and again, we'll go through it again in when we get back from spring break. But we're going to have a better idea April 3rd what the actual test will look like. So if you guys want to stay on top of things, it might be a good idea to follow along. But again, you can have access to this video, so you can come back and look at it whenever as you're preparing. Okay. So a couple things. I'll just first off, let me throw it out to questions. Are there any questions from yesterday's stuff or anything before we get into the new stuff in Unit 7? Feel free to ask questions now if you have any questions at all regarding anything not Unit 7 related before we get into the Unit 7. Okay. So feel free to ask questions, either email me or any questions from yesterday or anything else before we get into the new stuff. And while we're waiting on possible questions, questions. So I did post kind of this new optional assignment. So today we're going to go over kind of the first part of the guided notes, not all of them, not at all, but enough that you can work on these practice problems in your textbook. I think it might be a good idea to look at some of these notes, especially right now, this first set of notes right here, the kinetics and rate laws review notes. You might want to look over these. This is kind of going to be a review of what we discussed today in your guided notes. And so this is probably the most important. The other set, especially like the integrated notes, where is it? Do I have it? Oh, it's the PDF. Yeah, the integrated rate law notes, you can feel free to go over those now, but we're not going to talk about integrated rate laws today. It's only going to be differential rate laws. But all these are kind of the, what do you need to know, like the basic stuff that you need to know for this course, for this unit in the course, okay? So I got those notes up there posted for you, and feel free to do these practice problems. Don't feel like you have to do all the practice problems. A lot of them are, especially the ones towards the end, they're a lot of the same thing, a lot of doing the same thing, just practicing doing the same thing. So if you get it, you get it. But if you don't, you might want to, come in on Friday's live stream. Well, I'll go over any questions you have on these practice problems here. Okay. Were there any questions? No, I didn't get any questions. Okay. So before we start, just one other announcement, and hopefully you got this email and it's posted on Blackboard, but I think it's important that you know this. So College Board is, they're starting their review material now. Hold on one second. I gotta plug in the, why isn't that working? My laptop. Okay, there we go. Laptop's plugged in. Okay, so College Board is starting their review today. So go into the College Board classroom and check out the things that they have posted for you. I think they're doing live sessions, live review sessions. So maybe you want to catch another teacher's, live session on again, our unit 7 is their unit 5. So if you're worried about unit 5, which is our unit 7, because we're really, I'm gonna try to teach you, online. Get another teacher's perspective on that kind of thing. Go in there, and start reviewing units 1 through 4 as well. Like, so all the structure stuff, all the intermolecular force stuff, all that stuff, periodic trend stuff. Go ahead and start, using College Board's review materials that they have up there. They have video question answer sessions, that kind of thing. So feel free to use that. Don't just rely on me as your only source for AP Chemistry review material, okay? Also, get back familiar with this if you haven't, because I have a feeling that some of your assessments when we get back from spring break, a lot of your assessments that you'll be graded on, I will be making and publishing on the College Board classroom, because I can set time limits and stuff like that, and you're not going to be able to get a PDF and share it with people and stuff like that. So just make sure, don't forget about your College Board login credentials, because once things become mandatory again, tests and quizzes and stuff might be coming from that classroom. Okay. So let's see, were there any questions? No questions? Okay. So let's go ahead and start. Let's see should I get my face out of here? Let me see if I can do that. Let me remove that. Let's just do one screen. I don't want to do that. I want to do that. All right, there we go. All right, so I'm just going to get my face out of here. You don't need to see it anyway. Just so you can see the whole PowerPoint as we start going through this stuff. But I just want to make sure, can you guys still hear me? I just want to make sure that's good. Okay. So let's go ahead and start Unit 7. I'm going to turn on the PowerPoint. Once I turn on the PowerPoint, I'm not going to be able to see your chat. So I'll probably stop the PowerPoint every once in a while to type some extra stuff in a Word document that you can see. And as we're going along, please ask questions. I know how the PowerPoints and the guided notes don't always match up, and I might go off on a tangent. Can you still see me though? I thought you can hear me. Okay, good. Why? Man, this delay is pretty tough. Okay. Let's see. Huh. Tried to take that off. Oh, okay, I see. All right. That's what I needed to do. All right. I think that fixed it. Hold on. Ready? Yeah. No. Uh, that's got to fix it. Come on. There we go. All right. I'm off the screen. Okay. So let's go ahead and start Unit 7. All right. So I'll get on the PowerPoint. I'll get off the PowerPoint. I might not be following the guided notes perfectly. So, just kind of go as we can. Okay. So, and if you have questions, specific questions on the guided notes that I missed, please ask. Okay. Okay. All right. So Unit 7, okay, or let's say kinetics is kind of a study on its own. Now it ties into equilibrium, and we're going to talk about how rate and equilibrium kind of coincide with each other. And like the main part is kind of Le Chatelier's principle. If we say the reaction shifts to the right, what we're saying is we're increasing the rate of the forward reaction, right? Or the rate of the forward reaction is greater than the rate of the reverse reaction, right? That's what a shift to the right means, and a shift to the left means we're increasing the rate of the reverse reaction greater than the rate of the forward reaction. Okay, so kinetics is just how fast reactions occur. Okay, and the different things you can do to a reaction to make it go faster or go slower, or what things will cause a reaction to make it go faster or slower. It's not about is the reaction favorable or unfavorable, right? That's thermodynamics. Will the reaction occur at this temperature or won't it occur at this temperature? What's favored at this temperature? The forward process or the reverse process, or neither or both or whatever. That's the study of thermodynamics, but it doesn't tell you how fast a reaction will occur. Okay, so what kinetics is the study of this rate of how fast a reaction takes place. Okay, and so the first part of kinetics is understanding what needs to happen for a reaction to take place, and that's collision theory. Okay, so the first thing we have to talk about is collision theory. And if you remember, we've done it with where I made now that I have the camera off, it doesn't matter, but you clap your hands together and we did the twist with the wiggly fingers, that example, okay? So what has to happen for a reaction to occur? Particles must collide, but what has to be true about the collision? It has to have the right energy Okay, we call it the energy of activation. Okay, the activation energy, it has to have enough energy really to break the bonds of the reactants. Okay, that's what it has to do, right? So when that collision happens, what needs to break the bonds of the reactants? So you have to have enough energy to break those bonds. So if you have very high bond energy, if you have strong bonds in the reactants, you're going to have a slow rate of reaction because only a small fraction of collisions will be able to overcome the activation energy of the reaction, right? So like strong bonds on your reactants would result in a high activation energy of reaction. Okay, so the collision must happen, must have the right energy, but it also has the right orientation. Okay, so collision must have the right orientation and it must have the right energy. And if it has those two things, then we call that an effective collision. An effective collision is a collision that results in the reaction taking place. The reactants have turned into the products. And for the reverse reaction, an effective collision would be the products turned back into the reactants. Okay? All right. So that's collision theory, right? So, if you think about it in terms of, it might be, as we start to review for the AP exam, think about structure, right? It's, when this molecule collides with this molecule, what's really happening? You really need to look on the electron level. You really need to look on the dot structure level. Well, if a lone pair from this molecule collides with a lone pair from that molecule, nothing's going to happen. They're going to repel each other, right? If the partial negative of this molecule interacts with the partial negative of the other molecule, they're going to just repel each other. No reaction is going to take place, right? So it's kind of understanding what orientation would result in a collision. And we could do a quick example of that real quick. If we're just looking at HCl plus NH3 yields NH4 plus Cl minus, right? Well, what's really happening is the lone pair from the nitrogen, right? Nitrogen has a lone pair on top of it, right? Collides with the H plus of the HCl. It doesn't collide with the chloride side. The chloride side has a negative charge, right? It's a polar molecule. So the negative side of this molecule, which is the nitrogen side and its lone pair, collide with the hydrogen side of this molecule, and the hydrogen goes with the nitrogen and the lone pair, but the electrons in that HCl bond stay with the chlorine, and so that's why the chlorine turns into a chloride ion. And because NH3 only gains an H plus and not the electron it's being shared there, it becomes NH4 plus. Okay, but that's the collision. So if the nitrogen comes in contact with the chlorine, or the hydrogen from ammonia comes in contact with the HCl, no reaction is going to take place. Okay. All right. So what is activation energy? It's the energy that must be overcome for the reaction to take place. It's the energy barrier between the reactants and the products. And again, what would cause a high activation energy? A high activation energy would be caused by strong bonds of the reactants, right? Because what has to happen in that collision of the reactants? The collision has to result in the breaking of those bonds. So the stronger the bonds, the stronger the collision has to be, right? Okay. So we know what these potential energy diagrams look like, right? This would be an exothermic reaction. I know it's exothermic because the products are lower in energy than reactants, right? That delta E right there is really delta H of the reaction, okay? We have three stages of a reaction. We have the reactants, we have what we call the activated complex or the transition state, and then we have the products, right? The products are over here. The activated complex slash transition state is here, and the reactants are here, okay? Well, activation energy is the energy difference between the activated complex, which is the transition state, and the reactant particles, okay? So from this part of the hill down to the energy of the reactants, that would be the activation energy of the forward reaction, okay? But the activation energy of the reverse reaction, if we're talking about the reverse reaction, these would be the reactants. And the activation of the reverse reaction would be the difference between the activated complex, again, which is the same thing in the forward and the reverse reaction, and that energy down to here. So So for some, it's not really a question that comes up a lot, but like if you have an endothermic reaction, right? How would an endothermic reaction differ? The energy of the products would be up here somewhere, right? It would be higher than the energy of the reactants. If you have an endothermic reaction's forward reaction always has a higher activation energy than the reverse reaction. For an exothermic reaction, the activation energy of the forward reaction is less than the activation energy of the reverse reaction. And then and that must, again, favorability really doesn't tell you about reaction rate, but having a higher activation energy, means the reaction might be less likely to be spontaneous. Okay, but anyway, we know how to interpret these energy diagrams, and then what happens when you add a catalyst? You lower that activation state, right, or the activated complex, right? You lower that activation energy. So instead of the top of the hill being way up here, it's somewhere down here. So it's still the same energy difference from initial to final, right? That energy difference doesn't change. It's just we lower the energy of the activated complex when we add a catalyst, right? And now more collisions have enough energy to make it over that hump. Okay? So I'm just going to see if there's any questions so far. We'll get back to it. I'm off the screen now. Okay, good. All right. Any questions so far? Are we doing good? I might be, making going off on too many tangents. Okay. Let's see. Okay, so if you want to speed up a reaction, right, you have to increase the number of effective collisions. So one way to do that is increase the overall number of collisions, right? And so like let's say 50% of the collisions are effective collisions. Well, 50% of 100 is smaller than 50% of 1,000. So you could just increase the overall number of collisions and you'll get more of them to be effective collisions. Okay. Not a higher percentage, but just more collisions. You'll get a greater total number of collisions, right? If you increase the number of collisions, you'll speed up the rate of reaction. If you decrease the number of collisions, you'll slow down the reaction, right? So things that increase a rate of reaction would be a higher temperature. Remember, our interpretation of a higher temperature is particles move faster. Well, if they're moving faster, they collide more often. And not only do they collide more often, they collide with more energy, right? Okay. So decreasing the temperature slows it down because there's less collisions and with less energy, and so less collisions can make it over the hump, right? So higher concentration. If you just have more stuff, right? You add more stuff to your mixture, you're going to get a greater number of collisions. And so again, 50% of 1,000 is greater than 50% of 100. So if I have 1,000 particles colliding, and 50% of those collisions result in a reaction, I'll get 500 effective collisions versus 100 particles colliding, and I'll get 50 effective collisions. So just kind of understand that more particles equals more collisions. I'll get more of them to be effective collisions, right? Smaller particles, meaning like if you have a solid, this only works with a solid, you increase the surface area, right? You break it up, you cut it up into strips, you pound it in like kind of a mortar and pestle. More salt will dissolve if you grind it up and put it in water versus if you just put it like a big brick of salt in there. So increased surface area means more collisions. Okay. You can add a catalyst. What does a catalyst do? A catalyst doesn't increase the number of collisions that's going on, but what it does is it lowers the bar, it lowers the activation energy. So now a higher percentage of the collisions have enough energy for the effective to be an effective collision. Okay, and then increase the pressure. Okay, and one way to do that is lower the volume. So again, increased pressure means more particles in the system, right? You could add more particles, and so that's really increased concentration. Or you force the particles that you have closer together. And that's also increasing the concentration, right? If you lower the volume, you're increasing the concentration. So just increasing the pressure is the same thing kind of as increasing the concentration. And it's also kind of the same thing as lowering the volume, right? If the particles have less space, they will collide more often, and that means faster reaction. Okay. Okay. Any questions so far? Just checking. Okay. So let's get into rates. Okay. So how do we study rates of reaction? How fast a reaction takes place? Okay. Well, the one, the probably the easiest way or the most common way to measure how fast a reaction takes place is measure the concentration of one of the things in the reaction over time. Okay, so change in concentration over change in time is how you get a rate. Okay, so and remember, it's always change is always final minus initial. So the final concentration of A minus the initial concentration of A, and then divided by how long it took, right? So the concentration of A went from 1 molar to 0.5 molar in 50 seconds. So 0.5 molar divided by 50 seconds would give you molarity per second, right? So remember, a rate is a measurement over time, like how a measurement changes over time, like meters per second is a rate of speed, right? So rate just means divided by time. So how do we get our reaction rate? It's usually amount over time, and usually that amount is measured in concentration. You could do pressure versus time, right? That would be the same thing. And another thing you could do is something that we haven't talked about because we haven't gotten to that lab yet, the light absorption lab yet. But you could measure absorbance versus time, because absorbance of light, how much light a solution absorbs is directly proportional to its concentration. So instead of just concentration versus time, you could measure absorbance versus time. Okay. Now, a couple things. For a reactant, we usually call it the rate of disappearance, because at time zero, you only start with reactants and you have no products. Okay. So for a reactant, we'll say, it might be like 5 molar per second is probably a high rate, but like we could say the rate of disappearance is 5 molar per second, which means 5 molarity per second. That's how fast the concentration is decreasing per second. And since the concentration is decreasing, that means that reactant is kind of going away in the form of a product. We call it the rate of disappearance. For a product, we usually call it the rate of appearance or the rate of formation. Okay, because the reactant's disappearing, but the product is forming. Okay. All right. So let's look. If we look at this chart here. So a couple things I want you to notice. So at time zero, notice all we have are reactants, right? And it's just one reactant, right? And notice that after 50 seconds, right, we lost, what would that be? 21, like, 0.0021 molar of this, but we gained 0.0021 molar of this. Why is the amount of NO2 lost equal to the amount of NO gained in that same amount of time? Okay, if you answered correctly, it's because look at the mole ratio. For every 2 of these lost, 2 of these are gained. Okay? But why did we only get half the oxygen that we got of NO? So we only got 0.0011 molar oxygen in that amount of time, but we got double the amount of NO. Why is that? And again, it comes back to that mole ratio. For every 2 of these, you only get 1 of those. Okay? So here's something to understand. You can get the rate of disappearance of a reactant, or you could get the rate of appearance or the rate of formation of a product. And if you know one of the rates of any reactant or product, you could figure out the rate of everything else in the equation. All you have to do is multiply by the mole ratio. Okay, so let's do that. So in the span of 50 seconds, right, 0 to 50, we lost 0.0021 molar NO2. All right, so let me show you what I'm talking about. Just real quick, hopefully. Okay, so let me show you what I'm talking about here. Okay, so if we wanted the rate of if we wanted the rate for NO2, was it NO2? Yeah. If we wanted the rate of disappearance for NO2, during that amount of time, from 0 to 50 seconds, it was 0.0021 molar divided by 50 seconds. So the rate of disappearance would be 0.0021 divided by 50. So 4.2 4.2 times 10 to the negative 5 molarity per second, right? So that's our rate of disappearance. That's our rate of disappearance that would be my rate of disappearance for NO2 during that time period, right? Well, how could I get the rate of appearance or the rate of formation for NO? All you have to do, so rate for NO during the same period of time, right, would be 4.2 times 10 to the negative 5 molarity per second. All you have to do is multiply by the mole ratio in the equation. Well, the mole ratio is 2 to 2. It's 1 to 1. So NO2 has the same the NO2's rate of disappearance is equal to the rate of appearance for NO. Okay, because they have the 1 to 1 mole ratio. What about the rate for O? Was it O or was it O2? Yeah. Okay. During the same period. Well, what you could do, again, you could do change in concentration of O2 over change in time. But you could also just say, okay, if I take 4.2 times 10 to the negative 5, and I multiply by the ratio, let's insert the equation. The ratio was 1 mole of oxygen for every 1 mole of oxygen for every 1 mole, every 2 moles NO2, right? So if we multiply by our mole ratio, which is there, and we get that from our balanced chemical equation. So why did I do that? Okay. So we multiply by our mole ratio, and that gives us our rate of disappearance, rate of formation for oxygen. Okay. So if you know the rate of appearance or disappearance for a product or reactant, all you have to do is multiply by the mole ratio to get the rate of disappearance or appearance for another product or reactant in that same equation. Okay. Does everyone get what I'm trying to say there? Hopefully. Okay. Now, another thing to look at here is notice how in the first 50 seconds, we gained 0.0021 molar NO, right? And so that means we lost 0.0021 molar NO2. But look in the next 50 seconds, from 50 to 100, we didn't lose the same amount. We lost less NO2, so that means we gained less NO. Does anyone know why that happens? Why it so if I measured the rate during this period of time was what 4.5, 4.2 times 10 to the negative 5. But if I measured the rate here during this next period of time here, the rate is slower. Why does the rate slow down? Why does the rate of disappearance slow down over time? Why does the rate of appearance for the NO and the O2 speed up or slow down as well? Why do the rates slow down? Does anyone have an answer to that? Anyone know why the rate of the the reaction slows down as the reaction occurs? Any guesses? All right. So it's because you have less particles. As the reactants collide and form the products, you have less reactant particles. So the less particles you have, the slower the reaction. Okay? No, it's about the number of particles, right? It's about the number of collisions that can occur. So you have less and less particles, right? And then eventually, like if we're talking about a system that can reach equilibrium and then the reverse reaction can kick in, then yeah, as you're losing reactant, you're also gaining reactant as the reverse reaction is happening, right? Does that make sense? And then eventually we get to a point where there is no change in concentration. The concentration stays constant, and that's equilibrium. Okay, but understand what's going to happen as the rate of the forward reaction decrease. So the rate of if you only start with reactants, right? The rate of the forward reaction starts out really fast and then slows down as you approach equilibrium. And the rate of the reverse reaction starts at zero because you have no reactants for the reverse reaction because you have no products, right? So the reverse reaction can't happen. So the reverse reactions rate is zero at the beginning, but then it will speed up as you get more and more product molecules. You get more and more product collisions for the reverse reaction to happen, right? Okay. So hopefully that makes sense. Okay, but like notice this is the rate of which we're losing. Okay, this is the concentration of nitrogen, and notice the rate in which we're losing NO2 starts out really slow, or starts out really fast and decreases, right? And because that's all we have, but as the reaction proceeds, we get less and less of those particles. But the rate in which we gain these, right, starts out at zero, and then we get more and more. And then eventually we get to where the concentrations remain the same, right? If we follow these curves along the way, eventually we get to the point where all the concentrations remain the same, and that's when equilibrium gets established. Okay? But notice the slope, right? Notice the slope of this line versus the slope of that line, the absolute value of the slope, right? Would be the same because the rate in which we lose this NO2 is equal to the rate in which we gain NO. But notice that we only gain O2 at half the speed, at half the rate, right? Does that make sense? Okay. Yep. Okay. Yeah. So Charlie, you got it. Okay. So let's look at this reaction, right? So notice the coefficients, okay? So this is the rate in which H2 is decreasing, right? We're following this line. That's the rate in which H2 is decreasing. What's N2 going to look like? Okay, just kind of think in your mind what N2 might look like. What would that curve look like? Right? Are we going to lose N2 faster than H2? Or are we going to lose N2 slower than H2? Okay. So if you said slower, you were right? Because we're losing 3 of these for every one of those, right? So this is what N2 would look like. And notice NH3, the coefficient's 2, so it's we're going to gain NH3 faster than we lose N2, but slower than we lose H2, right? Does that make sense? And so what would that curve look like? And if you guessed it, it's right here, right? It's going to go that way. Okay. And then eventually, like, so what's this point? If they're all flat right here, what's that point? That's when equilibrium gets established, right there. Where it's not where the rates remain constant. The rates are equal. The rates do remain constant, but the rates of the forward and the reverse reaction are equal so that the amounts of the products and the reactants remain constant, right? That's what equilibrium means, okay? All right. So what's the instantaneous rate? It would be the rate at any given time. So what we're going to be doing is kind of like the average rate. That's usually what we focus on. So like we like are like what's the rate during this time, and what's the rate during that time, and what's the rate during this time period? Because the rate changes, right? We notice like the rate. It's not when you look at the rate in which we lose something, right? The rate in which we lose it, it decreases. The rate in which we gain it decreases, right? So it's increasing, but how fast it's increasing slows down, slows down, slows down. It's decreasing, but how fast it's decreasing slows down, slows down, slows down. Okay, so how do you get an instantaneous rate? Well, what you would have to do is uh, graph the plot the line and get the slope of the line tangent to the curve. Do you guys know what that means? The line tangent to the curve. So like if I wanted to know the instantaneous rate of disappearance of hydrogen at this point in time, I would have to write a line tangent to the curve, which is a line that only hits the curve at one point, and the slope of that line would be the rate in which hydrogen is being consumed at that point in time. Okay, does that make sense? Now you're not going to have to do it. You're not going to actually have to do that, um, but you have to explain it. So if you're asked for an instantaneous rate, the answer is get the slope of the line tangent to the curve. Okay, does that make sense? Okay, um, and that's your answer. Okay. Okay, so I think that kind of explain like so again, how do you measure rate of reaction? It's usually so it's amount versus time, like amount over time, right? Amount divided by time. Usually that amount is molarity over time, but it could also be pressure. So sometimes you might see atmospheres versus time, and it could be absorbance, how concentrations that have different colors absorb light differently. And so you might see absorbance versus time. And I'll explain that more when we go through the Beer's Law lab. Okay? All right. So there's two types of rate laws. There's the differential rate law and the integrated rate laws. We're just going to focus on differential rate laws today. And a differential rate law shows how the rate of a reaction depends on concentrations. Okay? So it's how the rate changes with differing amounts of concentration. So if I start with these concentrations, how fast is my rate going to be? But if I start with half those concentrations, how fast is my rate going to be? Okay. If I increase the concentration of just this reactant, how is that going to affect the rate? If I increase the concentration of this reactant, how is that going to affect the rate? Okay, so differential rate laws is how changing concentrations affect the rate. Okay, integrated rate laws tell us how the concentrations of our reactants change over time. Okay, but we're just going to focus on differential rate laws today. Okay, so what is the differential rate law? Okay, it shows us how the rate depends on the concentrations of reactants. Okay, here is a sample rate law. Okay, all right, so when you're asked to write a differential rate law, this is exactly what it's going to look like. Okay, right here. Whoops, let me go back. Okay, it's going to say rate. So if I say, hey, write the differential rate law or write the rate law for this reaction, you're going to say rate equals lowercase k, not capital K, lowercase k. Lowercase k is the rate law constant. It is not the same thing as the equilibrium constant. Now, if you know one, you can find the other, and we'll talk about how they tie in together. Okay, but right now, just understand lowercase k, rate law constant, not the same thing as equilibrium constant. Okay, so you would write rate equals k times the concentration of all of your reactants, okay, raised to the nth power. Now, that n right there does not necessarily mean the coefficient of the reactant. N is called the order of the reactant, and we're going to talk about what that means in a second. But you can only find N through experimental data. You can't find N through a balanced chemical equation unless you know it's an elementary step. And again, I'll tell you what that means down the road. So don't just blindly put 2 here because the coefficient of NO2 is 2. Maybe it's 2. It's 2 if NO2 is what we call second ordered, but only if it's second ordered. Okay? So this is the setup. So let me show you a little bit differently on your note handout. Right? This is what, again, this is the construct right here of a differential rate law. So if I ask you to write the rate law, okay, all you do is say rate equals K and then times the concentration of each reactant. So in this case, we have reactant A, reactant B. If there was another reactant, then you would do the concentration of reactant C. Remember, brackets means concentration. And the only numbers you actually have to fill in, the only thing you actually have to fill in is what N and M are equal to. Okay? All right? If A comes out to be a first order reactant, then you'll write a 1 here. If B comes out to be a second ordered reactant, then you would write a 2 here instead of M. That's how you find that's what a differential rate law looks like. Okay? So let's go to this one. All right? So again, if this is my reaction, if this is my reaction and I asked you to write the rate law for it, you would just say rate equals K, and it would be concentration HCl times the concentration of NH3. All right. And the only thing you would have to figure out is what the orders are. Okay. And the orders can only be 0, 1, or 2. That's it. And if it's 0, what's anything to the 0th power? Anything to the 0th power is 1. Okay. So anything to the 0th power is 1. So if something is actually 0 ordered, you don't need to include it in the rate law. But let's say you were told that these are both first order reactants, then this would be your rate law right there. Now, 1's understood. If you want to, you could put a 1 there and make it an exponent, right? I just got my button there. Okay. So if they're both first order, that's there. Now, 1's understood, so you didn't need to write it. If you were told that if that's my reaction, and I'm told that both my reactants are first order, that's my rate law. And if all I was asked was write the rate law, that's all I would write. Okay? That's it. I'm done. Okay? If you were told HCl was first and NH3 was second, then you would have to just change this to a 2. And that would be my rate law. If they were both second order, then you would change this to a 2. Okay? What if HCl was second order but NH3 was 0 order? Then you would say NH3 to the 0 power, and it wouldn't be in the expression. So that's another thing to know, guys. Another thing to maybe just write down here, and I think I might come up in the guided notes later. If you notice a reactant is not in the rate law, that means that reactant is zero ordered. I think the right way to say it is zero ordered. Okay. All right, does that make sense? Like, so if I like, you know, as we try to like tie some of this stuff together, right? If I say here's my reaction, here's the rate law, I'm telling you NH3 is zero ordered. Now you don't know what zero ordered means yet. We're going to talk about it, okay? But just kind of this is what a rate law would look like, okay? You don't know what zero ordered means yet, but we will talk about it, okay? All right. Let's see. Any questions so far? Going back to the chat, any questions so far? Notice that in a rate law, you don't include products, okay? You don't use products, okay? You can only use reactants, okay? So it's not something over something else. It's just the concentration of this raised to its order times the concentration of that raised to its order, you know, and so on and so on. And if it's zero ordered, you don't have to include it in the expression because anything to the zeroth power is 1. Okay. You can include it. You can have like you could put like the concentration of NH3 raised to the 0 power if you want to, but usually if it's a zero ordered reactant, it's not going to be included. Okay. Any questions so far? All right. Okay. So let's talk about what it means to be zero ordered, first ordered, whatever. Okay. Um, all right. Okay. So again, okay. Before we get to orders, just understand. Like, so if this is my rate, right? Whoops. Sorry. Okay. So if this is my rate law for a reaction, then I know A and B are reactants of that. Any other reactant would be zero ordered, right? Because it's not included in the rate equation. So what does N represent in this setup? N is the order with respect to A. M is the reactant, is the order with respect to B. Now there's also something called the overall reaction order. The overall reaction order is the sum of the reactant orders. So in this case, I would take N plus M, and that would be my overall reaction order. So if you're asked for a reaction order, not a reactant order, a reaction order, okay, you take the sum of the reactant orders. All right. So if we go back to our example, right? If they're both first order, right? If they're both first order, then like so you might be asked what like if they say here's my rate law, okay? What's the what's the order of the reaction with respect to HCl? With respect to just HCl, it's first. It's first order. If it asks with respect to NH3, then you would say it's first. But if it says what's the overall reaction order, it's 2, 1 plus 1. All right. The sum of the reactant orders equals the reaction order. Now we're gonna talk about the significance of that later. Right now it's just kind of just get okay. The mass reaction order, I just add the reactant orders. Okay. Okay. We're gonna talk about what that means soon. Okay. All right. So back to here. Okay. K again is the rate law constant, and then again, something in brackets is just the concentrations, right? Okay. All right. So hold on. Let's skip over the method of initial rates. Let's talk about what does it mean to be zero ordered, first ordered, or second ordered? Okay. So if you remember, what is a differential rate law telling us? It's telling us how rate depends on concentrations of the reactants. So if I add a little bit more of this, how is that going to affect the rate? If I take away a little bit of that, how is it going to affect the rate? Well, think about it. Zero ordered isn't in the expression. So what would that mean? It means zero ordered reactants concentration doesn't affect the rate. Okay? So you know a reaction is zero ordered when you change the concentration of the reactant, but the rate of the reaction stays the same. Okay. All right. So what is a zero ordered reactant? A zero ordered reactant is a reactant that you change the concentration of, but the rate of the reaction is unaffected. And you might say, well, wait a minute. I thought if we increase the concentration of reactants, that always increases the rate of the reaction because it increases the number of collisions. Okay. And so before unit 7, yeah, I would say yeah. Okay, but now what I'm going to say is it really depends on the reaction mechanism. What part of the reaction mechanism are those particles taking place in? What part, when do those collisions matter for that reactant? Okay, so right now what we're saying is just because you double the concentration of one reactant doesn't necessarily mean that's going to speed up the reaction. If the reactant is zero ordered, it's not going to speed up. It's not going to change the reaction rate. Okay. So how do I know something's zero ordered? I changed the concentration of it, but the rate stayed the same. That's how I know. Okay. All right. Well, what's a first order reactant mean? Okay. Well, you're going to be first order when you double the concentration of the reactant and the rate also doubles. Whatever change you make to the concentration, the same change happens to the rate. Okay? Hold on. You guys will get a kick out of this. I got a text from one of my college friends just now because I told him I had to go do a chemistry live stream. And he gave me a Tommy Boy quote. If you guys know what Tommy Boy is, um, Tommy Boy's a movie with Chris Farley. He was kind of a big fat guy from Saturday Night Live. Funny guy. Um, and he just texted me and said, "I heard the camera adds a couple 100 pounds," because that's a quote from Tommy Boy. It's a funny quote. Anyway, I got a kick out of that. All right, back to I got an alert from my phone, and I thought one of you might have had a question, but no, it was just my old college roommate with a fat joke. Anyway, all right, so back to reactant orders. Okay, so a first order reactant is a reactant that whatever change you do to the concentration, the same change happens to the rate. So how are you going to know? Again, you can only determine if a reactant is first, second, or zero ordered experimentally. So what do? You do a trial. You say, okay, you say, okay, I'm going to mix A and B at these concentrations and measure the rate of the reaction. Then the next trial, I'm going to keep B the same, but I'm going to double A and measure the rate. Well, if the rate also doubled, then now you know A, you doubled the concentration of A, and the rate also doubled, you know A is first order. Okay? So a first order reactant is one that whatever change you do to the concentration, if you decrease it, the rate's going to decrease by the same factor. So if I cut it in half, the rate's going to cut in half. If I quadruple the concentration, the rate's going to quadruple. If I make the concentration 8 times more concentrated, the rate of the reaction is going to be 8 times faster. Okay, that's what first order reactant means. Okay, and then second order, if you understand, like the order becomes the coefficient. So if I double the concentration of a reactant, but the rate quadruples, which is doubled squared, right? Then it's second order. Okay, so whatever change you make to the concentration, if that same change squared is what happens to the rate, then you know your second order. So what does that mean? What if you triple the concentration? Well, what's 3 squared? 9. That means if you triple the concentration and it's second ordered, then the rate's going to be 9 times faster. That's what we mean, okay? Well, what if you cut it in half? If you cut it in half, what's 1/2 squared? It's 1/4, right? So if you cut the concentration in half, the rate is going to decrease by a factor of 1/4, or the rate is going to be 1/4 of its original value, even though the concentration is only half of its original value. Okay, does that make sense? All right, so that's what that means. Okay, all right. So again, if you triple the concentration, the rate will be multiplied by 9. Okay, so let's do some of this practice here. Okay, it is found that A is first order, B is second order, and C is zero ordered. So there's my reaction. Okay. First, what's the rate law? Okay. It would be rate equals K times the concentration of A times the concentration of B squared. Would I include the concentration of C? If I did, I would have to have the concentration of C raised to the 0 power, but you don't have to include that, right? Does that make sense? Okay. All right. Okay. And then the next part, what will happen to the rate if you quadruple the concentration of A? Well, okay, well, A was first order, so whatever change I do to A, that's going to happen to the rate, so the rate's going to, the rate's going to quadruple. Okay. And then what will happen if you cut the concentration of B in half? Okay, I don't know if you can see that or not. But it would be 1/4 of the original value. And the reason why it's 1/4 is because B is a second ordered reactant. Okay. So let me stop at that example real quick and just, are there any questions there? Any questions? Any questions there? Any questions with that sample problem? And guys, we're almost, just in case you're wondering, we're almost done with today's stream. I'm going to show you one example problem on how to take data and get the rate law, and then you can work on those practice problems, and I'll go over any questions you have on Friday. Okay. All right, so we'll go back here. Again, any questions? Okay. All right, so we go back to the PowerPoint real quick. All right. So what will happen to the rate if A and B are both doubled? Well, let's think about it. If A is doubled, it's first ordered, right? A is first ordered, so the rate will be multiplied by 2. But B is second ordered, and if I double B, then I'm going to quadruple it. So I'm going to be multiplying by 2 and multiplying by 4. So the rate would be multiplied by 8. All right. Does that make sense? That it would be 8 times faster than its original. Okay. What will happen if C is increased by a factor of 10? Oh, wow. Nothing, because it's 0 ordered, right? The rate will remain the same. Right. Now, here's the question. What will happen if A gets quadrupled, but B is cut in half? So A quadrupling, A was first ordered, so I'd multiply the rate by 4, but B's cut in half and B's second order, so then I would multiply by 1/4, and what's 4 times 1/4? 1, the rate will remain the same. Okay. Any questions with those there? Okay. All right. So we'll do one more example here, and then I'll ask if you have any questions, and then we will call it quits. Okay, so how do you take lab data and get the orders? Okay, so for this one, okay, So we're asked to determine the rate law. So let's set it up, right? So here's the setup, right? This is the setup, right? I have three reactants. So I have potentially three different things in my rate law, right? So I have the rate law constant, then I have the concentration of my first reactant raised to its order, the concentration of bromide raised to its order, and the concentration of H plus raised to its order. So I have to figure out N, M, and P. So I wasn't told what they were. But we have this data to go on. So how are we going to get there? All right. So let's talk about it. All right. So again, what's not seen here is here this is trial 1, trial 2, trial 3, trial 4. Okay. So how am I going to figure out bromates? Okay, BrO3 minuses order. Well, look at what you do to the concentration and look how it affects the rate. Okay, does that make sense? Okay, now what we have to do is we want to look for two trials. If I want to figure out the rate or the order of this reactant here, just this reactant, I got to find two trials where I change its concentration, but the concentrations of everything else remain the same. Okay, so for bromate, I'm looking at trials 1 and 2 because I doubled the concentration of bromate, but bromide stayed the same and H plus stayed the same. Okay, so I doubled the concentration of bromate. What happened to the rate? The rate also doubled. So what does that mean? It means bromate is first order. Okay, so just real quick. So we figure out BrO3 minus is first order. We doubled the concentration and the rate also doubled. Right? Okay. So we got to do the same thing for the next one. So I'll just keep it like this. All right. So for the next one, we want to find bromide's rate or order. Okay. Well, we got to find two trials where we change bromide, but we don't change bromate and we don't change H plus. And if you look at that, that's trials 2 and 3. Look at 2 and 3, bromate stayed the same, 0.2 and 0.2. 2 and 3, H plus stayed the same, 0.1 and 0.1. But we doubled bromide. So we doubled bromide. What happened to the rate? 1.6 to 3.2. It also doubled. Okay. So now we know bromide is first order. Okay. Now we look for H plus. Now, where are the trials where we change H plus, but we keep the others constant? Does anyone see the trials? Does anyone see what two trials we should compare? Where H plus changes, but the others remain constant? Yeah, I'll go back to number 6 here in a second, okay? Um, I'll go back to number 6 in a second, Maddie. But just let's finish this one. Does anyone see the two trials I should compare to figure out the order of H plus? Does anyone see which trials they are? Whoops, didn't mean to do that. Okay, I think we're good. Okay. You want to see it? So if we go 3 and 4, let's look at 3 and 4. But then see, like we can't compare 3 and 4 for just the H plus because yeah, we changed H plus, but we also changed bromide and we also changed bromate. So the two trials you should compare are 1 and 4. Look at 1. 1 is 0.1 for H plus, and it's 0.2 for at trial 4, and then bromide stays the same. This trial to that trial stays the same. This trial to that trial. So we should be comparing 1 and 4. Okay. So if we look at between trials 1 and trial 4, bromate stays the same, bromide stays the same. We double H plus. We doubled H plus, but what happened to the rate? It went from 8.0 to 3.2, 8 point, or so 0.8 to 3.2, right? 8 times 10 to the negative 4 to, so 8 to 32. So what did it do? We doubled the concentration. The rate quadrupled. So what does that mean about H plus? Right? It means H plus is second order. So H plus. Okay, what did I do? Not responding, of course. Why did that happen? All right, so H plus is second order. Okay, I don't know why that document's not responding. Word's not responding. Okay. So H plus is second order. So I want to type it in here. So that means 1 would go there, 1 would go there, and 2 would go there. Now the ones are understood, so you don't need to write 1 there, and you don't need to write 1 there. But that would be our rate law based on this data. Okay. So does everyone see how to take the data and get the rate law? Okay, if you can do that, that's what some of the last practice problems on that problem set that I posted are just practice doing that. Okay, taking the data and getting the rate law and answering questions. Okay, so hold on, I got a couple emails here. All right, yep, Charles got it 1 and 4. Okay, all right, good. All right, so let me go back to, was it number 6 in the first example? Right. Whoops, I keep pausing it, sorry. All right. So again, we found H plus is second ordered because we doubled the concentration, the rate quadrupled. All right, so let's go back to number 6. Okay, so number 6. Okay, so remember, for that question, we were told that A is first order, B is second order. Okay, and we want to know what happens to the rate if A is doubled, or no, quadrupled, sorry. Quadrupled, and B is cut in half. Okay. Okay. So A quadrupling. So what will we do to the rate? So we would do the initial rate that we had before, we changed the factors times 4. So I would multiply the rate by 4 because I know it's got to quadruple. Why do I know it's got to quadruple at least? Because A is first order. And if I quadruple A, the rate's going to do the same. So I would take my rate, I would multiply by 4. But I changed B as well, and I cut B in half. Well, B is second order. So 1/2 squared is 1/4. So now I got to multiply the rate by 4, but I also got to multiply it by 1/4. So essentially, I'm just multiplying it by 1. So the rate will be unchanged. So what we're saying is the change with respect to A would quadruple the rate, but the change with respect to B would cut the rate by 1/4. It would be 1/4 of its original rate. So both those changes negate each other, and so the rate would be its original rate. Okay, does that make sense, Maddie? Does that answer your question? Okay, good. All right, so that's it for today. We're going to talk about other things. I don't know if I'm going to stick to the PowerPoint or whatever. I might have new material to introduce, but so here's kind of the deal. We need to do differential rate laws. We need to talk about reaction mechanisms, and then we need to talk about integrated rate laws. And then there's a couple of labs that we need to talk about that also kind of go with kinetics. And that would be this unit, okay? Well, Aaron, remember we did do collision theory, and we talked about rates to speed up reactions and stuff like that. But we're not rate laws, no. Differential rate laws, integrated rate laws, no. But collision theory, potential energy diagrams, yeah, we've covered that stuff, but not differential or integrated rate laws. Okay. But anyway, so we're gonna do that. I strongly suggest you to, go ahead and skim through chapter 14. You don't have to like heavy read through chapter 14, but just look through chapter 14. Okay. Look over the notes I posted and try those practice problems. At least read through the practice problems and like, you're like, oh, okay, I know how to answer that. Or if I don't know how to answer that, or give it an attempt maybe. I'm going to post the key tomorrow, and then I'll be back on Friday to answer any questions that you had on those practice problems. And then we'll start into maybe reaction mechanisms and how to interpret them. Okay. And really, it's really different ways to find the differential rate law. So right now, how can we find the differential rate law? Right now, we know if I just tell you what the reactant orders, you could just write the rate law expression. If I give you the data, right? That was the very last problem I did. If I gave you the data, could you find the rate law? And then the next thing we're going to learn is if I give you the mechanism, if I give you the reaction mechanism, how do you find the rate law? Okay. So just all three different things leading you to the same result. And then we also need to do some practice. You're also going to have to solve for K. All right. Eventually you have to solve for the actual rate law constant. But we'll talk about that later on. Okay. So right now that's a good intro to rates. Go ahead and try your practice problems if you have some time. And also, if you're bored, you need something to do. I guess I can recommend Tommy Boy, the movie Tommy Boy. If you haven't seen it, it's a classic comedy. Chris Farley, David Spade. It's a good one. All right. So anyway, have a good day. Thanks for joining, and smash that like button. All right. I'll talk to you on Friday, but I'll be posting stuff tomorrow. So check that out. All right. Bye.